Okay, we're design team 6 doing the ECE480 and Stellaris control cards for motor driving applications. I'm L.T. Thomas.
I'm TJ Lewinsky.
I'm Pat O'Hara.
I'm Cole Reese. Okay, we're going to give you some background of the DRB8824 EBM and the DRB8824 IC. Then we're also using the ECE480 microcontroller, so we're going to talk about that, give you a little bit about the architecture and some of the features. And then we're going to talk about the Stellaris, which is another microcontroller, and give you some background of the software that we're going to use. And then we're going to go over what we did to try to solve it and where we're at in our solution, and talk about our budget, which is kind of interesting. And go over the risk analysis, and tell you all the ways our project could possibly fail, and go over our agenda and where we're at right now. Okay, so our project is based on the DRB8824 EBM, this thing. It can drive a maximum current of 1.6 amps, and it can drive 2 motors. The main components are the ECE480 microcontroller right here, and the DRB8824 IC, this thing right here. It implements a number of protective features, overcurrent protection. So in case you try to draw too much current, it'll automatically shut off and won't fry your board. Short circuit protection, temperature protection. If you were gonna implement it in like a car, we have fluctuations in temperature. For the actual DRV, it will shut off. You won't be able to, fry whatever circuit you have. Applications to ATMs, printers, and anything that has a motor, basically. This is the outline of the actual DRB8824 IC. It has 2 H bridges on it. This is the H bridge structure. It's actually implemented with MOSFETs. So these switches, the MOSFETs are configured as switches. Basically how it works, the voltage through the motor is proportional, the speed of the motor is proportional to the voltage through it. So when these switches are on, you'll get some voltage and the motor will come on. But how motor control works is that the ECE480 will send some pulses to these switches, which controls the rate at which they turn on and off. And it will control the average voltage across the motor. So by controlling the average voltage, you can control the speed. As I said, it's regulated pulse width modulation, and it can operate at a maximum frequency of 500 kilohertz. Our design task is that right now we only have 1 microcontroller. We can only control it with the ECE480 microcontroller. So Texas just wants to make the design more modular. So we're gonna put a DIMM slot on the board so that we can operate it with both the Stellaris and the ECE480.
Alright, so I'm Pat O'Hara. I'll be talking about the 2 microcontrollers that we'll be using in our project. The first one that we're using is the ECE430. The ECE430 is a mixed signal, meaning it has both analog and digital components on it. We will be actually using 2 analog signals in our project. But it's a 16-bit RISC architecture. What RISC means is a reduced instruction set computing. The idea behind that is that a simpler instruction set can produce lower power but also faster execution of the instructions. So the ECE430 is generally used in low power, low cost applications. And some applications would be like wireless, like a wireless application or an embedded system. So the one that we're using has an 8 megahertz clock, 55K of RAM, and 5K of flash. So pretty small requirements there. But the important things that we have is it has 1 12-bit analog to digital converter, and then 2 12-bit digital to analog converters that we use. And then it also has, for pulse width modulation, it has three signals that we can use for pulse width modulation. Those are 16-bit, which is more than what we need. It has 5 power saving modes. What that allows is run really low power, and you can shut off different parts of the chip. So when it's running at about 1 megahertz, it's at 330 microamps, but you can turn that down to in a low power saving mode to about 0.33% of that. And then you can also turn off the chip completely, and that saves, drops it down to about 18% of the low power saving modes. This is a little bit of what it looks like. In the low power saving modes, you're actually going to shut off the CPU completely. It's in all the modes. And then to differentiate between the other 5 modes, you're going to turn off your main system clock, your digital oscillator, and your main oscillator over here. So the next microcontroller that we're using is the Stellaris. The Stellaris is the Cortex M3, which is an ARM architecture. It's still a RISC architecture, and the difference between the ARM architecture and the MSP430 is that it allows for both 32-bit instructions and 16-bit instructions. So it makes it a little bit easier for porting code. We can still use 16-bit instructions if you wanted. And then there's also Thumb and Thumb 2, which allow for mixed 16 and 32-bit instructions together. The Stellaris is also used for low power applications because, like I said, the ARM architecture allows for lower power but faster speeds. This microcontroller has 80 megahertz clock, 256K of flash, and 96K of RAM. So we have a little bit more room to work with. And for pulse width modulation, which is what we'll be using, we have 4 blocks that we can use in this chip. And each block will give you a pulse width and then also the complement of that.
Hi, I'm TJ Valinsky. I'm going to be talking about the software background in our project solution. TI has given us the DRV board plus the code for the MSP430. And going through that code, what we found out is that code's structured, so any type of board can be used. What they do is they just declare a lot of variables and have a case statement for each of the different types of boards, like the 8824 or the 8812, and then it just has a list of tasks with each one, and we'll just execute that. Our PC will connect to the DIMM card through USB. That uses an RS-232 standard, which is a 3-pin using as a transmit, a receive, and ground pin. That's how it'll communicate with the DIMM card and how we'll program our microcontroller. This is a picture of the Windows application that we will be using to send signals to our microcontroller. We can send signals such as the step, which is just the frequency and how fast the step's going to happen, the direction of the motor, and mode. There's mode 0, mode 1, and mode 2. Mode 0 would cut the frequency in half, mode 1 by a quarter, mode 2 by about 1/8. Okay, now for our project solution, this picture on the left is the original DRV board that we were given. And this section right here is the digital section with the MSP430 right there. What we're going to do is remove most of the things in this circle and put it on a DIMM card. And then we replace it with a DIMM 100 slot on that board for our final board. Things we don't remove are the JTAG, which is this area right here. That's used for debugging. And then right below it is 2 resistors. Those resistors, like I explained how before in the code, how the program would pick which board. By changing the values of the resistors and then just changing the driver controller, that's how the program would know, but the different values of the resistance, how the program would know which motor or driver controller to use. Okay, and then now for making the control card. We were given the Stellaris control card, which is in the top right. This is a control card that they used last year in the project. So we went through the Solaris card and figured out how they map the pins, and we're going to have to map the pins similarly in the MSP430 control card. And what we found out is this first section of pins is the RS232 pins, the transmit, receive, ground. There's also 3.3 volts coming in from USB, those pins. This section is a bunch of the analog pins from the MSP430. The most important section is the pulse width modulation pins right there. Those would have the step signal, the mode signal, and direction signals. The next section is the general purpose input-output. Pretty much we're going to assign the rest of the MSP430 pins there that aren't really vital to our design. And then the last section is the JTAG pins. There's, I think, roughly 4 signals coming in there that are for debugging. And then roughly through the analog to the GPIO, there's roughly a ground and a 5-volt pin every 5 pins.